What if I told you that a nursing student just built a pharmaceutical database containing 660,000 pages of drug information, dosage calculations, and clinical protocols, and they did it all using Claude Haiku, the cheapest AI model available? Not Claude Opus, not GPT-4, the budget option that costs pennies per query. And here's the kicker, it took them just 3 weeks to build something that would normally require a team of pharmacists and software developers months to complete. If you think you need the most expensive AI to do serious work, this story is about to change your mind completely. This video is for anyone who's been told they need premium AI subscriptions to build something meaningful, whether you're a student, healthcare professional, researcher, or anyone working with large datasets on a tight budget. By the end of this video, you'll know exactly how to use Claude Haiku to process massive amounts of information, create structured databases, and build practical tools that actually solve real problems in your field. I'm going to walk you through the exact methodology this nursing student used, the prompts that made it work, and the 3 critical mistakes most people make when trying to scale AI projects like this. I've been testing AI productivity workflows for over 2 years, and what you're about to see represents one of the most impressive budget AI projects I've encountered. Let me paint you the picture that led to this breakthrough. Sarah, a third-year nursing student, was drowning in pharmaceutical information. Every clinical rotation meant memorizing hundreds of drug interactions, dosage calculations, contraindications, and administration protocols. The traditional resources were scattered across textbooks, online databases, and clinical handouts, none of which talked to each other. But here's where it gets worse. The existing pharmaceutical databases cost hundreds of dollars per month for student access, and even then, they weren't customized for nursing-specific needs. Sarah needed quick answers to questions like what's the maximum safe dose of morphine for a 68-year-old patient with kidney disease, or which antibiotics interact with warfarin and what are the alternative options. She was spending 3 to 4 hours every night just cross-referencing information from multiple sources. Multiply that by thousands of nursing students worldwide, and you're looking at millions of wasted hours that could be spent on actual patient care skills. The problem wasn't just about time, it was about having reliable, searchable, nursing-focused pharmaceutical information in one place. Traditional solutions would require either paying for expensive subscriptions or somehow convincing a software company to build a custom database, neither realistic for a student budget. Enter Claude Haiku, Anthropic's fastest and most affordable AI model. While everyone's obsessing over Claude Opus and GPT-4, Sarah discovered that Haiku's strength isn't in creative writing or complex reasoning, it's in rapid, accurate processing of structured information. And at roughly 25 cents per million tokens, it's practically free for projects like this. Her approach was brilliantly simple. Instead of trying to build one massive database in a single query, she broke the pharmaceutical universe into manageable chunks. She identified 7 core categories: basic drug information, dosage calculations, drug interactions, contraindications, administration routes, patient-specific considerations, and emergency protocols. The workflow looked like this. First, she'd feed Claude Haiku a specific drug category with a detailed prompt template. Second, she'd have it generate comprehensive information in a standardized JSON format. Third, she'd use a simple Python script to compile everything into a searchable database. Fourth, she'd spot-check the output and refine her prompts based on any gaps or errors. What made this work wasn't the AI model, it was the systematic approach to prompt engineering and data structuring. Sarah treated Claude Haiku like a really smart research assistant who needed clear instructions, not like a magic database generator. Let me show you exactly how this works. Sarah's master prompt template looked something like this. You are a clinical pharmacology expert creating a comprehensive drug database for nursing professionals. For the drug, provide the following information in valid JSON format: basic information, generic name, brand names, drug class, mechanism of action, dosage information, standard adult dose, pediatric considerations, elderly adjustments, renal/hepatic dosing administration, routes available, preparation instructions, infusion rates if applicable, interactions, major drug interactions with clinical significance, food interactions, contraindications, absolute and relative contraindications, nursing considerations, monitoring parameters, patient education points, adverse effects to watch for, emergency information, overdose management, antidotes if available. Format your response as valid JSON with clear field names. Be specific about dosages and include units. Focus on information most relevant to bedside nursing practice. She'd then run variations of this prompt for categories of drugs, starting with the most common medications like pain relievers, antibiotics, and cardiovascular drugs. Each query would return 15 to 20 drugs worth of information in perfect JSON format. The genius was in her quality control system. She'd batch process 50 drugs at a time, then use a simple Python script to validate the JSON structure and flag any incomplete entries. When she found gaps, she'd refine the prompt and rerun just those specific drugs. For the actual database compilation, she used a basic SQLite setup, nothing fancy, just something that could handle the structured queries she needed. The Python script would parse each JSON response and populate the database tables automatically. Here are the 3 advanced strategies that made this project work where others fail. First, the progressive refinement technique. Sarah didn't try to get perfect results on the first pass. She started with a basic prompt, processed 100 drugs, identified the most common gaps or formatting issues, then refined her prompt template. She repeated this cycle 5 times, each time improving the consistency and completeness of the output. Most people give up after the first imperfect batch, but the magic happens in the iteration. Second, context chunking for complex interactions. When dealing with drug interactions, where one drug might interact with dozens of others, she didn't try to capture everything in one query. Instead, she'd process drug interactions by therapeutic class, then use a separate pass to identify cross-class interactions. This prevented Claude Haiku from getting overwhelmed and missing critical interactions. Third, the verification sampling method. She couldn't manually check 660,000 pages of information, but she could spot check. Sarah created a random sampling script that would pull 50 entries per drug category and cross-reference them against established pharmaceutical references. This gave her confidence in the overall accuracy without requiring manual verification of every single entry. When her spot check showed 95% accuracy or higher, she knew the prompts were working. So there you have it, a nursing student just proved that you don't need the most expensive AI tools to build something genuinely useful. With Claude Haiku, smart prompt engineering, and a systematic approach, she created a pharmaceutical database that's saving her hours every week and could revolutionize how nursing students access drug information. The key takeaway here isn't about pharmaceuticals, it's about thinking systematically when you're working with AI on large projects. Break it down, iterate your prompts, and focus on structure over creativity. Whether you're processing legal documents, research papers, or any other large dataset, this methodology will work. If this video helped you see AI productivity tools in a new light, hit that subscribe button. The links to Claude Haiku and the tools mentioned are in the description below. And let me know in the comments